All right, fellows, now we come to the data deluge. This is just the enormous amount of data that is going on all around us. And this is the second lesson of this set into motivation of this big data applications analytics course. We will see that actually these sites tend to be on the old side because actually people no longer focus on the data deluge. They focus on what you get from the data. So no longer are these joyous descriptions of how many petabytes, exabytes, or zettabytes of data you're getting. They're telling you all about how many decisions they made using big data. But still, it's very amazing and important to document the amount of data there is. So let's get going. Thank you very much. So this is the KBCB chart from which they update this every year. They don't always put the same slides, but they have this type of slide every year. And then 2014 end of, which is around here, we're up to nearly 9 zettabytes. Beginning of 2016, 13, and around 16 zettabytes towards the end of the year. All right. Notice that the largest science is around 100 petabytes, which is an amazingly small fraction, 0.4025 of the total. If we want to understand what a zettabyte is, what if we have 100 gigabytes on your laptop? Typical amount today may be of that order. That is 10 to the 10 laptops. It's a zettabyte, and remember we have 9 of them. An exabyte is a pretty big number. That is 1,000th of a zettabyte. A petabyte is also a pretty big number, and that's a 1,000th of an exabyte. And finally, we get down to terabytes. And remember, that's the size of disks, and you can buy these 2 terabyte disks for about $90 today. And terabytes comes gigabytes, 1,000 gigabytes. And remember, a few 100 gigabytes is a typical piece on laptop storage. Note that an interesting number about some interesting feature of 7 zettabytes, it's about a terabyte per person. Pretty interesting. There's a terabyte per person on the internet today. So this explosion, huge numbers, is what's driving the data deluge, data science, the fourth paradigm, the cloud computing, and so on. Okay, here is a 2016 chart that updates the previous one. I actually think that the chart is wrong. It measures billions of petabytes of data. I think it is millions of petabytes of data. Otherwise, you won't agree with the previous slide that the total is measured in zettabytes, whereas zettabytes is a million petabytes. Anyway, here is the amount, which is getting up to 10 zettabytes here in 2015. But this slide also has another thing going on. It's showing the exactly opposite curve, which is the cost of storage, which is going down from 18 cents here per gigabyte of storage back down here to 6 cents in 2015. Actually, the cost of storage seems to be decreasing more than the amount of data, saying that we can actually store a larger fraction of the available data today than we could in the past. Anyway, it's quite striking how storage technology is advancing so fast. Because again, this is the type of thing in the past people said would not happen. We couldn't do this type of thing. Then technology would slow, Moore's law would stop, and then we couldn't store as much data. And we would have a challenge as the amount of data increases and our ability to store it decreased. Here's just some minor detail from a nice service, business intelligence. This has the total cloud traffic in zettabytes per year. It's sort of interesting. This is the natural unit. And we have mobile cloud. This is, of course, pointing out the mobile cloud traffic is increasing more rapidly than the total. It's still a small part. Many people think that not so far in the future, mobile will be the dominant use of all personal traffic. That's this thing I pointed out, that multi-core is making clients smaller. And therefore, only things like my poor old eyes are getting old and they don't like such terribly small screens. That's all that's keeping these personal devices small. Meanwhile, they're going to have smartwatches and Google glasses and heart sensors and feet sensors and all what's have you, all helping me and providing the wearable me. So here we are. Cloud traffic increasing significantly every year. This is standard Moore's law exponential. Here's this 1.8 billion photos per day uploaded. And the remarkable thing is you can't see poor old Flickr, which is probably the best known of these various services. There's a tiny yellow sliver here you can see. Blue is dominant, Facebook, and then suddenly in 2013 up comes WhatsApp, and well, here comes Snapchat, with Instagram, which is part of Facebook, I believe, hanging in there. So, amazing number of photos uploaded every year, and as I mentioned, poor old Kodak once, was the dominant film supplier, and people took photos lovingly, and they filled shoe boxes full of photos, and that was the unit of number of photos owned by a person. But now with the cloud as is, you can fill many digital shoeboxes or virtual shoeboxes or electronic shoeboxes in the sky. This slide here updates the previous one with another year. Actually, it has 2 solid years because this comes from 2016, 2 complete years going up to sort of, I don't know, 3.3 million photos per day. Quite impressive number, showing rapid rise in WhatsApp, the light blue. Snapchat is possibly slowing a little. Messenger is bursting in the scene, onto the scene, and Instagram is not doing so well. And Facebook is plugging away, the core Facebook. Of course, it's really quite striking to see how the world of photography has changed due to the incredibly impressive cameras they now put on smartphones and the way anybody uses their smartphones. And so previously, you needed your single lens reflex or what have you camera. It was a large chunky thing. Now you can get comparable quality with as many pixels on a large thing sort of this size as you could on as you now can on a smartphone. So implicit in this image growth is incredible technology growth. The IoT for this being the cameras on smartphones. All right. And as a companion to the previous slide on photos from the social media side, here we have the actual messages themselves. I recently got a WeChat login because I was told everybody in China uses WeChat. And so as I was in China, they wanted to talk to me. I had to install WeChat, which actually works perfectly smoothly. Fine system. But if we look here, you can see WeChat is somewhat below Messenger. Facebook Messenger has a more rapid increase, and WhatsApp, which is the largest of these systems. To an old-fashioned person like me, the interest in messaging as opposed to email, it's sort of curious because email is not that different from messaging, and yet it's an email. I actually don't have a graph of the growth of email, but I do not think it's growing significantly as the messaging systems are. And I'm not quite certain why you couldn't have an email system that was as effective as these messaging systems on messaging. So anyway, that's That's a sort of slightly different. And meanwhile, anyway, this is just an example of the digital technology and the digital transformation changing the way people live their lives. Okay, here is a corresponding YouTube figure. We have 20 hours 6 years ago. That's around here, 2009. We have 100 hours around in 13, and actually 14 seems to be similar. I don't quite understand that, whether it's leveled off or this prediction here was a little inaccurate. But if you go to this YouTube press release site, it still says 100 hours of video uploaded per minute. It would be actually interesting if it leveled off, because YouTube, although it has many competitors, is still a pretty important dominant service with many people using YouTube, including this course, using YouTube to deliver its message. Here's an interesting thing from KDCB about music. So here we have streaming. Remember, this course is streaming. We don't have music. We have my harsh coughing voice, and here we have digital tracks, presumably sold online, but digital. And here we have physical music sales. So everything is declining except streaming music. People don't even want to store their music locally on their iPod or whatever they used to store it on. They just want to have their smartphone or phablet or tablet or maybe a window on their PC and just look at listen to the music or look at the digital TV and web TV, and that's it. That's presumably the future. And this is all part of digital disruption. The way of doing business is changing. We know there was a huge fight in the music business about this. And probably both sides won in the sense that the digital version actually dominated and effectively won, although now you can see it's actually going down, but replaced by this. But in the end, artists did get paid. Not everything is free. You have to go to iTunes or Google Play and buy a lot of the things you want, with just some things offered free. This course is offered free, but I'm not a rock music star. Here's first of some slides about sizes. So in every 60 seconds, this is actually still a little old, but in every 60 seconds you have whatever it is, over 300 new Twitter accounts, 100,000 tweets. Tumblr is actually increasing a lot recently, so that's probably wrong. iPhone applications, Flickr, which we know is negligible, 1,700 Firefoxes, 700,000 searches, 168 million emails sent every minute rather, and 60 blogs, and 70 new domains registered, and so on. These are just fascinating numbers here. The trouble is actually to keep up to date, to keep this slide, which is beautiful. I don't know any place that keeps these slides up to date. You just see them every now. They're produced in some heroic effort, and then they're not kept up to date. So that's life. Still, they're impressive. Here's another version focused on actually U.S. government data. Here's U.S. Geological Survey. Here is the global IP traffic from Cisco, and it's sort of interesting. It's measured in 225 exabytes per month. It says per year you have zettabytes of IP traffic, and that goes nicely with the zettabytes of data stored. Here's the Department of Energy, and here, remember, we have 15 petabytes a year is some measure of the amount of data from the Large Hadron Collider. Here is the global wearables. Remember, this is meant to be 25 to 50 billion by 2020, and we're according to this at the moment. Well, actually, see, these numbers are not consistent. Cisco has a larger number, but anyway, it's 2020. They make it as 20 billion. So what do we have here? EOS disk is that's a classic Earth science storage from satellites. Here we have the NIH explosion coming from gene sequencing. Um, we have that's here and here. This is NIH, this Cancer Institute. Here we have Internet of Things. So here's the Internet of Things. Oh, sorry, this was wearables, which is a subset of the Internet of Things. Obviously, Internet of Things lives in cars, lives in street signs, street monitors, and so on, lives in homes. Here we have NOAA, the climate and weather people, and here's that data increasing. And here we have DoD with drones pouring out data. What it says, 43 terabytes per data per drone. That's because cameras are digital. They take their data and they get more. Just Moore's law says those little CCDs get smaller every year, and you get more pixels and therefore more data from your drone. So this is a pretty interesting graph from Scalarity.com. So now we come to an analysis of a book called Taming the Big Data Tidal Wave, a variant of the data deluge, a tidal wave of data. And this is 2012 book, already old, sort of, from Chief Analytics Officer from TERADATA, which is a major database company. And he covers the following industry-oriented, business-oriented applications, web data, which he calls the original big data, where we know that data from how people browse websites is actually used, gathered and used in all sorts of ways to motivate mailings, to redesign those sites, to do recommender engines, to suggest from your browsing what else you might want to look at, and so on. Auto insurance was discussed here. We can have sensors that monitor the driver, or actually less obtrusively the cars, and the information about what the cars are suffering from the bad driving can be automatically recorded and analyzed, maybe to set insurance rates, and maybe also to help drivers drive better. And also, of course, mend cars by identifying errors before they actually happen. There's a lot of forms of text data, of which email is the most simplest example. Sentiment is analysis of tweets as text data. Here we have natural language processing. And also there's an example which we do in the introduction from eBay, where they analyzed how people purchased lamps and were able to improve the interface from just looking at what people did and what they ended up doing, so they could more quickly point you at what you wanted. One of the biggest, and actually this is one of the 51 use cases, big data applications is logistics, or analyzing truck fleets, or delivery fleets, or for its military and commercial and consumer applications, where GPS data can track all these things, vehicles, trucks, people, and so on. That's GPS. We have RFID, which is sort of a tag which allows you to do better manufacturing logistics because you know where everything is. We have the smart grid, which is the electrical utility industry. And the smart grid can analyze local usage in a building and tell that building how better to make use of, do what it's doing. And it can also monitor the actual power as it transfers through the network, and then make the network better used. There's the gaming industry, where you can look at RFID tracking chips, and that can help you identify fraud. We have, just after this, analysis from GE of industrial engines, which is sort of the industrial internet, and the sensor data, and how that's an enormous amount of data can allow you a far more reliable monitoring of large equipment. Video games is a little like the web data example, and even the auto insurance example. You have telemetry, which is monitoring what's going on in the case of users, and this is monitoring how people play games to actually design better games and see what people like. And there's a whole broad social media example, which is the telecommunication industry and the Facebook and so on. And the linkage of people to people allow you to find new customers automatically from, again, recommender engine-like technology. Here we have the GE example I mentioned. So in 2012, who knows whether that's still accurate, GE were gathering 7 times the data of Twitter. And so GE engines are a big data source, and that data is used to just monitor the health of the equipment. It's a very nice example of the industrial internet, which there are several. You can find quite a lot of interesting discussions of that, because it's not just GE. GE has set up, in fact, a whole new software endeavor in Silicon Valley because of the importance of the industrial internet. Here's a little more detail. They have 25,000 engines. They have 3.6 million flight records per month. And each of them has 200 parameters, 18 million parameters per month. And this allows fuel efficiency, aircraft space capacity analysis, and produces all sorts of improvements to the aircraft and the engines. And it basically improves the whole maintenance process. Hopefully will make customers happy because they identify failures first. And this is a pretty nice talk. I have a link down here from a talk at Berkeley, which is I strongly recommend. So here is a summary of some sizes from science and technology. We've already done the 15 petabytes per year for Large Hadron Collider. Radiology is big, 69 petabytes per year. There's a thing called the Square Kilometer Array Telescope, SKAA, which is half a zettabyte per year of raw data in around 2022. Usually these are a little optimistic. Earth observing is still quite small, only a few petabytes per year. Earthquake science is nowadays actually terabytes more. Polar grid is hundreds of terabytes per year and is growing very rapidly. This is due to the improvement of the radars, which are just every time you improve your radar, you add more channels, you get better resolution, you gather more data. An important application is just looking at the results of simulations. So you have these computers doing simulations. You can take a collection of simulations and a collection of results, analyze those results to get much more insight. Actually, that's actually a pretty good example of machine learning. And that's around a tenth of a zettabyte per year from an exascale simulation. Here's a nice example from NIH. And this is a famous one. Here's the cost to sequence a genome. Here we have $100 million for the first genome in 2001, not so long ago. And now we have down here a little around $1,000 at the budget genome sequencing organization. And what's striking is here's this cost to analyze the genome, and now we compare it with Moore's law. And so the cost to sequence a genome is drastically decreased by many orders of magnitude, maybe 2 or 3 orders of magnitude is decreased by 3 orders of magnitude more than the cost of computing, which says then to analyze this data for a given amount of it's going to cost 1,000 times as much, because from what it did in 2001. So something which was dominated by the effort of gathering the data might now be dominated by the actual processing, the actual analytics run on the data. And this is going to lead to 100 petabytes or so per year if you, for instance, decided to sequence everybody. Here's an interesting curve highlighting an important issue which will come out from several points of view. Here is called the long tail of science. And that says there are some fields like particle physics, that's the LHC, astronomy, the S square kilometer array, and LSST. And here's biology, and these are plotted about. These have a few experiments, each of which is very large. That's this up here. And then we have over here, we have the long tail, economics, social science, some biology, where you have individuals gathered doing lots of experiments, but they're not got a lot of people involved and not a lot of data. So we have a few large data things, and then we have a lot of small data things. A lot of small data is the so-called long tail. Long tail is very suitable to clouds because clouds are very effective at analyzing lots of things, each of which is not so big. They're not so effective at analyzing individually huge things, because then you need to use parallel computing. And for some things like search and recommender engines, clouds are very effective parallel computing engines. For other things like clustering, they're not so effective. So this type of graph is also seen when you look at books sold. There are a few books which sell an enormous amount, and lots of books which sell a small amount. And now if you run a physical bookstore, you sort of cut off here. Now you only have space to hold this. And the person going to the physical bookstore never sees this. This is why the internet allows, it's sort of more democratic. It allows the long tail to be accessed. And using recommender engines, you can actually suggest which part of the long tail people should look at. Pretty interesting. So here are some data-intensive activities. From my point of view, I gave you the TERADATA fellow Franks' view. Particle physics, which is a bag of events. Information retrieval is a bag of words. I'm trying to point out there's always a space attached to each of these activities. E-commerce, a bag of items to be sold, or users trying to buy things. Social networking, a bag of people with links and properties. Health informatics, a bag of health records or a bag of gene sequences. Sensors, lots of pixels, bag of pixels. And these applications here use statistics, deep learning, image analysis, recommender engines, or anomaly or outlier detection. And they do this on cloud. So this slide here really gives you a nice example of a rich set of fields in a different set of spaces with a range of tools all running on clouds, and they're using variants of MapReduce. And this comes to our famous summary of the course, the big data ecosystem in one sentence. We're using clouds, we're running data analytics, we're doing it collaboratively, all working together, we're processing big data, and we're solving problems in X informatics, or EX. EX informatics is a superset of X analytics, and here are the values of X we discovered on the web. And we noted there's some like physics which weren't actually defined. We hadn't used the term informatics before, but should. And of course, we're doing data science, and that's what this course is all about. And it's an exciting new academic area which captures all of this. And here is the final slide of this this lesson. Remember, this is lesson 2 of Unit 2. And this is from the web what I collected. Here are these definitions where I found people had introduced the concept of X informatics before. Originally, around when I first came to Indiana University, I taught my first class called X informatics and got attacked because people said it's not a good idea. And then I stopped until I stopped for about 10 years and gave up that course. Oh, well, I mean, sometimes you have good ideas and you have them too early, or you give them up too early, you're too sensitive, and so on. Here we have earth science informatics, pathology informatics, lots of other medical informatics here, health informatics, biomedical informatics, medical informatics, biochemistry, cheminformatics, biology, and so on, bioinformatics. Here we have energy informatics, lifestyle informatics, which isn't quite the same lifestyle as I use it, but it's at least there's a university in the Netherlands that can study that, environmental informatics, and a much bigger field, social informatics. All right, there we are. Informatics and X-informatics. You can get rich. You can just cure cancer. Do whatever you want with X-informatics. And all you have to do is learn a bunch of algorithms, buy a few clouds, and you're home. You have everything you need to do X-informatics. And of course, you better get a degree in data science because that's the qualifications. So here I am signing out of lesson 2 of unit 2, the motivation. Thank you.